All right, good morning everyone. Today's lecture is going to be on radiographic testing, but I wanted to just follow up with a couple slides from the discussion we had yesterday on ultrasonic testing. So I had discussed the automated inspection system they had in Ohio at University of Dayton Research Institute. I wanted to show you the actual system here. So this is, I believe, a 5 or 6 axis similar to what's known as a Faro arm. So it's in industry, sometimes it's known as coordinate measuring machines, but it is an automated system that operates in various dimensions. And what you're seeing in the image here, this is the water bath, and this is the component under inspection. So the transducer would actually be sitting somewhere up here, and it comes in intimate contact with an encoder, so it knows its XYZ position, and then the scan operates without human interaction. So I had mentioned one of the important things to have before you try to automate the inspection is the scan plan. So what you're seeing in this bottom image here is after the scan plan was put in, programmed into the system, you see this is where the transducer and wedge would move on top of the sample, and you're inspecting from the what would be considered the base of the wedding cake sample rather than the top. So these are the various layers, and the system itself identifies it as hit or miss, and that's what you're seeing by these red indicators here for the various layers. So that was the automated system. We had discussed phased array, how you can have, rather than a single element transducer, you can have many transducers, and you can steer the beam by time lapse on when the various transducers send their wave. So if this was a longitudinal wave that was just had a transducer that was pointing down on the sample, this is where you can get your sectorial scans that were shown in the sample yesterday. And the width of that arc of the sector depends on how many active elements you send at a single time. So for this case, it's sending 16 elements at the same time, and this would be your area of interest that comes out in the C-scan data. And you would actually move the wedge and the probe along the surface. So some of the commercial units have up to 128 elements. So what it does is it automatically uses Snell's law, and it sends a time lapse that is programmed into the element for each active transducer. And that way, when it goes into the program, it knows the time lapse between elements, and it gives you more data simultaneously. That previous slide was for a longitudinal scan. So the other type of scan would be a shear scan at an angle. So what you're seeing here is a 45-degree wedge. So that means your transducer is interrogating through the sample at an angle. And if you took that and looked at it schematically, what it is doing is would be the area of interest. And this is where you can get, if this would be your titanium or aluminum alloy, what you'll be seeing in this wavefront would be the scatter or the attenuation of the various acoustic waves as it goes through the thickness. So some of the latest and greatest that is now coming out into commercial, there's a couple techniques. One is called full matrix capture, and then the other is called the total focusing method. So now that this has been commercially available for 10 or 15 years, they have a better idea on sources of noise and scatter for various materials. So they're using different ways to increase the resolution of the data output. So that's just from a conference I was at, a vendor in the US that sells a system that it basically integrates the data a different way so you can get the full matrix capture. The other thing I wanted to discuss from probability of detection, So we talked about how you get your confidence levels and the sensitivity versus reliability question. So there's actually a software system that you can download for free, and it's from Mill Handbook. So the government put it out for aerospace industry. And this is just kind of a brief discussion of how you would actually program this POD software if you were doing some type of statistical analysis in your research. So that you can take a look at as well. So that was just a follow-up from yesterday. Did anyone have any other questions before we start with radiography? Last image was, this was from the immersion tank at UMass Dartmouth. So what you'll be seeing here, this is actually C-scan data. So the C-scan data is actually the image, the colored image that you'd get, versus the A scan or B scan, which would just give you amplitude versus distance. And what you're seeing here is those flat bottom holes. But one of the interesting things from this particular image was there was some other features on the surface due to residual stresses and due to the way they included the laser beam holes in there. So we actually were able to see some areas that were somewhat subsurface due to the surface prep in the ultrasonic image. So for radiographic testing, yep. Did you have a question or?
No, I will ask you later. It's a longer one.
Okay. So for radiographic testing, has anyone ever broken a bone, had to get an x-ray? All right. So one of the most famous images in terms of radiographic testing was from W.C. Röntgen, and it was actually when he did the x-ray of his own hand. So if you look in a lot of non-destructive testing books or in the ASM manual, you'll see the radiographic image of the person's hand. So this was 1895, and for today's discussion, we're going to talk about both X-rays and gamma rays. So we're going to be talking about energy levels in this range here. One of the things in industrial sites when you're doing radiographic testing on large structures, whether it would be a submarine or a bridge deck or something like that, when you need to get sources higher than X-rays, you'll go to a gamma ray source. And I can touch upon it today, but the source, the isotope used for the source varies depending on how much energy you need to interrogate the sample. One of the things to note, so the radiographic testing began in the medical industry, but it's been used for semiconductors, nuclear, automotive, aerospace, and other industries. So it began as a technique to look at human body, but the technology's been transferred to look at metallic components. There's a big difference when you have to scan something in the body versus metallic. So it's the KEV that you need to penetrate through. So one of the things you're going to see in some of the later slides is there's a system that's at Harvard that we'll talk about. It's 225 KEV unit, and you'll see in some of the images that I discussed yesterday, based on the longest dimension, if you cannot fully penetrate the sample, you'll see the noise that you get in those images. So if you only have to scan the human body, all right, we're only talking about 1 or 2 KEV, something on that range. When we're talking metallic components, it's 50 to 50, 200, 450, depending on how the longest dimension is. So a background on how X-rays are generated, okay? So one of the things is, has anyone in here used scanning electron microscopes in their lab work? It's very similar to how the SEM accelerating voltage works, okay? You have X-rays, they're fired at a high speed onto the target. the speeds can be up to 0.8 speed of light. So the electrons are being fired very quickly. The majority of them are not being absorbed. So less than 1% of the X-rays actually have enough energy to produce X-rays. The rest becomes heat. The rest gets dissipated as heat in the sample. So using proper cooling is critical for X-rays that are not going to be something where it doesn't matter if it's cooled or not. If it matters if the sample is being cooled, and if the sample is being stationary, generally you'll want to have in the system, this is a cabinet type system that's self-enclosed, some type of cooling so you don't overheat the target. As I said, in order to get energies in the 30 to 450 kiloelectron volt range, we're sending electrons at velocities 0.8 c, so 0.8 the speed of light. The other thing to note that you have to operate under vacuum. If you don't have the system under vacuum, then the X-rays will scatter before they even hit the sample and you won't get any output. So in general, you have to pump the system down to about 10 to the minus 7 atmospheres in order to keep that vacuum sample and actually get the X-rays to be absorbed into the sample. All right, upon contact with the test material, there's deceleration, and that deceleration results in heat for the most part. And then for less than 1%, the electromagnetic radiation becomes X-rays. Due to that high heat that gets dissipated, the choice of materials in the system is important. So for the anode, you generally use a tungsten type material because it has a high melting point. For the sensing material, which is whether if it's traditional film X-ray, it's the film itself, or whether it's computed tomography, it's that target screen. That material is also critical based on the cooling. So for digital radiography, which you're going to see some images, they use amorphous silicon or amorphous selenium rather than a film material, where if you're at the doctor's office, they put the film and they put it under a white light and you can see the contrast. With what you'll see in these later images for the digital radiographic images, they use this selenium or amorphous silicon material. So one of the things I discussed before, when you're using radiography and you're looking at large structures, you need to have proper containment so that the X-rays don't come into contact with humans in the vicinity of where the test is occurring. So this is important. This is probably about 1 or 2 meters worth of a concrete bunker. And when they're actually doing the inspection, they'll have in the labs, they'll have lights going off so people don't come within the area. If you're at a job site or out in the field doing this, they actually have to evacuate the area of other people working. So this ties into the cost of inspection. If the other workers can't do welding or other field applications while the test is happening, that all ties into the cost of doing the inspection. What you're going to see here, this is your source up here, and the source shoots the X-rays down. These are 3 turbine blade samples similar to the sample here. And this is for digital radiography. So rather than the output being a piece of film that you'd look at, what happens is where the X-rays get captured, it basically leaves an imprint on this base material. And you'll see in the next couple slides, they take that and they put it into a computerized system, and it actually reads the readout right off of there. All right, so this image here is the quality for a film. This was actually a piece of film that was put on, viewed under a viewer, and then just a image taken of it. So you see a lot of noise, and there's issues with contrast and brightness in the regular film. And one of the things is you can only take one shot with the film. If it's not in focus, then you'd have to then reset everything and then take the film again. So it takes more time. With using digital radiography, you can actually reuse this radiographic film between 200 and 5,000 times. So there's a higher cost for the materials, but you get that back by being able to reuse it multiple times. This is actually, when you look within that what was laid down for the sample, this is either the amorphous selenium or this is the material that is in the digital radiograph component. This image here, we talked about it yesterday. This was the sample where the machining blade broke off during boring out the center. So what you're seeing is it wasn't able to bore through the whole center of the sample. So we saw the back side of it yesterday for the UT samples where the machining blade was embedded. This would be the other side. So for this type of radiograph, you actually shooting from the top down rather than with the UT would have been flipped on the other side. So the direction of the scan is different based on these two techniques. And you can see based on the image, this is the same blade as was in the slide before that I showed with the contrast and the noise for the film. With the digital radiograph, you can actually put more samples at the same time, and you actually can get a better contrast for the internal cooling channels. So you can see the internal cooling channels. You can also see this is what's known as dovetail attachment. So this is where the blades actually fit into the disc on the rotating turbo machinery. And you can actually see the internal areas of the dovetail attachment as well. This is important for aerospace because the dovetail attachment is known to be an area of high stress, and over time they can get cracks from the inside of the cooling channels down in this attachment area. So it's important to be able to see these internal components. All right, before I go further, just a couple things about the basics of X-rays. Sources of noise in the X-ray, all right? So 3 main sources of noise that affect your X-ray image quality. The first one's called unsharpness, and in the industry, it's known as penumbra. That's based on the distance between the source and the sample, and also has geometry, and it also has thickness implications. And then contrast and resolution. So depending on whether you're using an X-ray computed tomography system or a film system, you want to try to get the most contrast you can. And this is because essentially it's a grayscale. You want to get the most variation and the biggest gradient in your grayscale to be able to see internal voids. So the unsharpness is defined as just the sum of various sources of noise in the system. So you can have noise due to the geometry. So the noise from this sample would not be the same as the noise from this sample simply because they have different thicknesses and then different features. You also have, for computed tomography, there's a source of noise because as opposed to film and digital radiography where the sample remains flat and you just send the X-rays onto the source, in computed tomography, the sample actually rotates 360 and it takes multiple slices of a single sample. So you have an added source of noise from the motion of the sample on the turntable. For certain samples, they use screens, so filters or screens to keep features of the X-rays minimized. And I'll show you these in later slides. Some of these features are known as beam hardening. They're aspects of the X-rays and from when they hit the target screen. So in order to minimize that type of noise, sometimes a screen is placed in between the source where that tungsten filament, they put a screen at the end of it to try to minimize. So if you were looking at aluminum, you can use a 1 millimeter copper screen to minimize the noise for this particular alloy. So that's a consideration that depends on the material you're looking at. And then the last factor is of the film itself. So there is some degradation if you're doing digital radiography, the more times you use that film. So if you're using it 3,000, 4,000 times, there is some degradation of the film itself just from multiple uses in service. So that can also be another factor of noise. So the total unsharpness, that geometry factor here, it's the effective width of the source. So that is your focal, that's the spot size. And for a traditional film, the spot size is different than for computed tomography. If you're using computed tomography, one of the advantages is that you can actually get a micron spot size, a focal point spot size. That is, if you're looking at things that are mesoscale, microscale, you can actually get resolution at the microscale. You can't really get that same resolution with traditional film radiography. And you can get it to a point with digital radiography, but it's still not as, the contrast won't be as good as computed tomography. So the two factors are the distance from the object to the screen and the distance from the source to the object. So how far, this is simple geometry, so it depends on the scattering based on how far the X-rays have to travel.
You say that you use a screen in order to reduce the noise. So how does it work? I mean, how do you choose the perfect thickness of the screen in order to get enough signal?
So the thickness of, so the example I'll use is for computed tomography. So if I was looking at this is like a 6000 series aluminum, I would either use a 1 millimeter or 2 millimeter screen. And the choice of the screen depends on the longest dimension. So this is the limiting factor, the longest dimension, because in the longest dimension, you have to have the X-rays fully penetrate and then come back. And that's one of the things you'll see in the images. That's one of the constraints of X-rays that sometimes they choose to use ultrasonics instead, because the ultrasonics does have better penetrating power. So if you have a very large sample and it's a dense material, if it's a steel or if it's a superalloy material, the longest dimension is gonna be a main constraint to the technique you can use to inspect. So that's the type of filter you'll use will be dependent on the material. But the main thing is you have to make sure that you can actually scan through the whole part. One of the things you're going to see here is, so this is this sample here under digital radiography. You see variations in grayscale as you go through the various layers. So there is sources of noise as there's more scattering from the X-rays as it penetrates further. So what you're seeing is you're still able to see certain drilled holes and side drilled holes, but it actually becomes harder to find the flat bottom holes at the base layers, just due to additional scattering as you're going through the layers of the sample. So one of the other examples I'll show you is this was a blade taken out of service, and the inspector at the site circles 2 areas here for additional evaluation. So the first scan, without doing any type of modifications to improve the image, you really don't get, you're really not able to discern where those flaws are. But you can actually adjust the brightness and contrast, and then by optimizing it, you're able to see those 2 areas in that bottom image. So there are ways to play with the brightness and contrast and the settings to improve the ability to find flaws. I mean, if you already know where the flaw is from visual, this would just be to confirm how far depth-wise it penetrates in. So it's on the outer surface, but the concern was there also some type of corrosion or wall loss on the inner surface? So that's why the choice was done to do X-rays for this sample. So the main thing I want to discuss today is computed tomography for the samples those sample I just handed out. The difference between the digital radiography and the computed tomography is you're able to take multiple thousands of 2D slices because the sample rotates 360 degrees, and then you're able to actually use rendering software to get a 3D CAD CAM model that you can then interrogate and look at various depths with the software. So the digital ability to look at internal flaws is one of the main advantages of the technique. It's not a new technology. It's been used in the medical industry for now probably closer to 30, 40 years. The first commercial system came out in 1972. It was a British engineer called G. Hunsfield, and it was used for medical imaging. Same thing, CT imaging in the medical imagery, it's CAT scans. But the difference is, in the CAT scan, if a person goes in for a CAT scan, the X-ray sources move around the individual. For industrial CT scans for structural components, the structural component moves 360, and the source and the target stay stationary. One of the restrictions, and we talked about yesterday, the cost of inspection, this would really be done, it has to be a high value component. So for aerospace industry, it actually is now being used because they can set up the blades and they can inspect multiple blades simultaneously. And for the cost of a blade, cost of one of these blades is between $5,000 and $10,000 as a final manufactured component. So if you wouldn't be using CT for a $5 plumbing part. So this is one of the images here for a schematic of what you're seeing in the CT scan. This would be a component under inspection, and this is what moves 360 degrees. Your X-ray source, so this, on the X-ray source, this is where you would put your filter or your screen, depending on what material. So if it was a nickel-based superalloy, you could use something other than copper. But for the samples I looked at, in generally, it was a copper screen. And then this is your detector screen, which sometimes there's silicon drift detectors or amorphous silicon on the, that's the material for the screen. So the screen doesn't move, the X-ray source doesn't move, but the part moves 360 degrees. There's systems available at various government labs or otherwise around the country where you can actually do large components. So we can do full Humvees, Army tanks, vehicles, And what you're seeing here is not a Humvee or Army tank, but this is probably 3 to 5 feet in the longest dimension. So as opposed to this, which is only inches, this is when you would use a gamma ray source because you need more energy to penetrate through the longest distance. The thing that is used quite a bit in industry is this technique is used for reverse engineering of components. So you're able to actually do what's called segmentation. If you have dissimilar metals or non-metallics in contact with metallic components, if you know what the approximate densities of those materials are, you can then set thresholds and you can color code the output based on the density. So if you thought you had an inclusion that was hard alpha inclusion and you knew what the density of that should be, you could actually use that to locate flaws within a manufactured part. It's used a lot of times in industry for porosity in castings or other high value components. So if you cast a component and you think that there might be shrinkage porosity or voids within the inside of it, you would have the idea because the density of that void is going to vary from the density of the base metal. And that's called a segmentation technique. So in this image here, you can see the various, it's color coded based on density. And it's very useful for reverse engineering purposes. So this is the system down the street at Harvard. It's a 225 kilo electron volt system. What you're seeing here is your source material. This is the cabinet box here. So this is lead because it is at such a high KeV. They use lead material, lead glass to shield the user from the x-rays that are generated. The sample would rotate on this turntable here, and then the x-rays are absorbed onto the detector, which you can't see in this image. So this is the detector right here. So this is where the x-rays actually get absorbed from the various scans. And this is the source. So an image of the source, when you have to actually change it out, it's similar to a scanning electron microscope when you can blow the filament out pretty easily on these if you don't adjust your contrast and brightness correctly. You can actually saturate the sample and cause the filament to blow pretty quickly. So this would be the inside of that source area where you would have to replace tungsten filaments. So there are consumables within the equipment itself. The output from the test on the sample I passed around, this is what would be the output on your user interface. The software they use is called VG Studio Max, but there's actually a few different types of rendering softwares that you can use. And one of the things you'll see is you see various orientations of the sample. So you have orientation top down, you have an orientation, basically a side view, a top down view. And this is where you can segment the sample and decide if you wanted to look at quarter thickness, half thickness, 3/4 thickness. You can do it much easily with this equipment than trying to do it from a manual technique. The dialog box is over on the right-hand side. What's important to note here, this is what determines what's known as the dynamic range of the scan. So this is all based on grayscale. So the grayscale, I believe for this was a 16-bit grayscale. So it's similar to if you have, a 4 HD television or something like that. It's rather than pixels, it's known as voxels, volume elements. And this is how you can actually adjust contrast and brightness in order to improve the resolution of the image. So one of the things that has a great effect on the output is where you decide to choose to put that dynamic range. So that is basically an option that a user has to select, and that deals with how many grayscale images and the differentiation and the gradients between the grayscales. If you don't do it properly, this is at the beginning of the test. All you're going to get on the output is a black image. So when you set up the sample, what you want to do is actually saturate the part that you want to inspect. And by saturating it, you're going to be sure that when it renders it, you're not going to have any dropped 2D scans. So the dropped 2D slices are when you don't fully penetrate the sample and the X-rays don't appear in the rendering. And it can make a huge difference if you're trying to use this for reverse engineering or for computer-aided drafting. If what you want is to get the 3D rendering, if you have dropped pixels, it will have a big problem with the output once it's computerized. So you want to saturate whatever sample that you're testing. If you don't saturate the sample, you can get various sources of noise that will really deteriorate the sensitivity. So in computer tomography, they're called slices. A slice is essentially just a single, if it was traditional film, the slice would be a single film. But since it takes thousands, 2,000 to 3,000 slices in the computer tomography, it brings them together afterwards and renders it. So this is if you didn't put the proper screen, right, for that aluminum, you would get this type of noise. This is why you use screens to reduce that noise. And they know these are sources of noise based on these equations above here. All right. Other types of noise for circular samples, you see these are called ring artifacts. And this deals with your focal points. So the ring artifacts, as the part moves, you can see that it's concentrically shown multiple rings. So there's ways to compensate for that as well. And the last one is for beam hardening. If you know that your X-ray beam, you know a certain X-ray you have to use. The beam itself, it can lose focus if it has a geometry that is not something circular or based on the geometry, you can get the beam hardening. So that for the beam hardening, this is where you can put different filters in to compensate for. For the samples I passed out before, so one of the things you'll see here, the system at Harvard was only 225 keV. For that aluminum sample, and you can see the size of it, for the aluminum samples, it was right on the cusp of being able to fully penetrate the sample. For that steel sample I brought in yesterday, the output was completely black. So that means that it was not fully penetrating the steel. For the steel, actually had to go to a different location where they had a system that was 450 kV. There's other systems that go up even further. But for that steel, the 450 keV was right on the border for steel. For the aluminum, that 225 keV, you even see that there's noise. So it was able to penetrate through the sample, but there's quite a bit of noise. So I couldn't improve the resolution of the scan. It would have probably had to have gone up to 300, 350 keV system to be able to get a better image. But what you can see here is for reverse engineering or for flaw detection, you can actually do that segmentation and take cutaway shots. So this would be halfway through the thickness. This is, you can actually take cutaway shots as the various layers. So if you know the thickness of the layers and you wanted to see a slice at that top layers, you can change that and look at that way. You don't have to look at all 5 of the layers. So that's a way to reduce noise by basically cutting out the layers that you don't need to look at. And you can look at the layers of different depths individually with this technique. So the sample I handed out, I'm not sure if any of you saw, but on the sample itself, there's like a dent in this area here. So this is just a close-up of that. You can see that the system was able to distinguish between that versus the flat bottom holes and the side drilled holes. So that's just kind of an order of magnitude on the resolution you can get for that CT system. And that's a product of the microfocal spot size. If you were doing film radiography, you probably would not be able to distinguish that at this sensitivity. So one of the things I wanted to show was for one of these turbine blades here. For presentations and conferences and things like that, it is nice that you can actually make basically rendered movies of the sample. So you can actually, you can show various views and get motion of the sample, which is important. So that sample there, that was the sample that I showed earlier where there's 2, you'll see those are the 2, these are the 2 areas that were pointed out by the inspector. So the CT scan actually shows them, it has more clarity than other techniques because of that focal spot size, that you can get a finer resolution of the microstructure. If we're looking at the individual angles, this is what happens if you don't fully penetrate through. So this was as we're trying to determine what X-ray was needed, I think this was something at maybe 70 keV. And if at 70 keV, you see the X-rays don't fully penetrate. So this is something that you have to, if you know what material you're working with, you can go look up what X-rays will generally be needed, but it is dependent on the longest dimension. And it's dependent upon, for this sample, there's internal cooling channels. So it's the scattering of the X-rays through the sample. When the X-rays scatter through, in the open void space, there's nothing in its path. But when it hits the inner wall and outer wall, there's other scattering. So this is what happens if you don't fully penetrate the sample at the appropriate X-ray level. These are different views you can get. So, this is what I'm saying here. This would be that void space up on the top where that's the inside of the blade. This is an example of where the technology is at. This is Fraunhofer is a institute, a lab in Germany. So they can put full vehicle in there, and you can distinguish between various parts of, your engine block versus your wheel well versus the body in white, which is what the structure of the contour is. So you can put entire components like this in. And the last thing I wanted to kind of touch on today is with respect to the reverse engineering. This is an example of an entire engine block. So what you're going to see here is an engine block has many different components and many different materials in the components. So the spark plug is not the same as the engine block itself. So what they're doing here for this motorcycle is they're disassembling it they will scan each of the individual engine components by itself. And those become separate files that they can basically just call upon that file once it's all rendered. So each of these individual components will get its own scan. And once all of the individual component gets its own scan, using the rendering software, you can make exploded views and you can actually show the engine being assembled and disassembled using the computed tomography technique. So you can't get this with digital radiography and you can't get this with film radiography. So this is them importing the individual parts of the engine by themselves. So this is just kind of a time lapse. Yeah, this is an entire semester project that somebody did. So as they're importing all the different parts, now they're essentially getting what would be a SolidWorks or a Pro-E mechanical model. They can then use these to do various renderings, and this is where the value with CT comes in, because once you have these, you can alter designs much more quickly than if you had to try to do full experiments of the engines. So for complex assemblies of various components, when the individual components are assembled into a larger structure, there's a lot of value for designers in using these techniques. So this is after they've done the individual CTs of these parts. They can then show in the SolidWorks model how it assembles back together again. And then what you're going to see, well, other than that, so this is after they've scanned all the individual parts and they've rendered it and reassembled it. Now this is what you would use if you were a designer. There's value to this industrially for both reverse engineering purposes to see what a different manufacturer of a similar component makes their parts out of, as well as if you needed to modify your design. So say there was a recall of a specific part in this engine, this would make your life a lot easier on your options for dealing with the recall or something of that sort. And then a program like this is not necessarily the rendering software for the CT program. This could be something like Camtasia Studio or a software that interacts with the SolidWorks model. So there is, for aerospace blades, they do this quite a bit for turbine blades, and there's actually industrial CT systems specific for blades. One's called Blade Runner, but that they know they need to have a certain KEV for those blades. So they've actually, for certain industries, they'll design the CT system around the component that is under inspection. So let me see if there's anything else. So just to end, a general comparison of the traditional film versus digital radiography versus 3D computed tomography. Some factors to take into account are the dynamic range, which I discussed, and then what resolution of the image. So do you need it to be on micron scale? Can it be 1/16 of an inch? That is going to be dependent on the criticality of the industry that's being used for. So that's just the last thing is, so this is what you'll see. This is what I'm talking about, the noise in film radiography. So this is from the traditional film, and you'll see that compared to the digital radiography, there's a lot more noise in those images. And because it's just a single shot. So if you don't get the accelerating voltage correct, or if you don't have all your variables correct based on these, you just have to redo it again, and that film, it becomes useless. With the computer tomography, you basically tailor it towards what component you're looking at. So that's what I wanted to end with today. Have a good week.